So maybe a radical type question. So here I have this peroxide. So that oxygen-oxygen bond, that's a kind of a traditionally weak bond that we break for radical reactions. So HV is just light, some sort of energy. Sunlight can do this, right? And what's going to happen is that bond is going to break homolytically. So we're going to get two new radicals. We call this the initiation step. Right, we're forming new radicals. So we didn't start with any we had no radicals to start. Now we formed radicals. And then here I drew an alkyl group, just something. And I'm going to have it react with this. So the question is, what H am I going to pluck off? Right? So we always kind of take off hydrogens in these things. And kind of like thinking about, and we're always thinking about the radicals we form. So this is a propagation step. So we're going to form, we start with radicals, we're going to form more radicals. But which hydrogen should we take? So we had a couple similar questions like this before. So there's hydrogens on all those carbons. Well, not all of them. Which atom is going to have a radical? Which carbon? Which number? 2. I like 2. 2. So how do we do that? We draw the H in, the hidden H. Of course, it's hidden. That's not fair or fun, but there it is. So we're going to take that H. So these two are going to meet. Right? Those two are going to meet. And this other electron is going to go to carbon 2. All right, and we made that. Nice things about carbocations, not carbocations. Nice thing about radicals, unlike carbocations, even though radicals are electron deficient, right? They don't have a full octet. They do not rearrange. So we don't need to worry about rearrangements or that kind of silliness. They can do resonance, but that's not the same as rearrangements. So then we have this radical, I don't know. We can have it react with whatever. Doesn't really matter. You want to do a termination step? We could do a termination step. We could say, so let's do a termination step. Radicals are really hard to control, kind of similar to carbocations. You can imagine they're not easy to control, right? Radicals, they have kind of these initiation steps, and then they go, and they're just gone. But one possible thing that could happen, probably not that probable, but hey, it could happen. So we'll draw it out. These two radicals find each other. And notice how we draw the bonds together. Right, when they're forming a bond together, they kind of meet in the middle. Right, they kind of meet in the middle. And we're going to make this ether now, I guess. And a lot of times with the radicals, you kind of got to know what you're trying to make because they can make lots of different things. So there's an initiation step. We create radicals. Propagation step, right, where we take radicals and make new radicals. Termination step, where two radicals come together to make no radicals. Biggest things, check your arrows, they come together, all those kind of things, and knowing those steps. So one thing that's hard about radicals, there's not really an electrophile nucleophile as much, right, because you're just kind of splitting the bond in two, right? So we don't get to do those terms, radical, the nucleophile, electrophile, as much, if at all. Yep, so we don't have those terms. Good questions. So there's a good question I just got about like ranking stability of these things. So when you're doing these like steps, it's not a matter of, well, I guess I could say this, right? So the O dot, an oxygen that it doesn't have a full octet, this is more reactive than the carbon that doesn't have a full octet. Does that make sense? Right, these initiation ones, when you make these it's like the match that starts the fire. So these are more reactive than this, right? But like, I'm not necessarily going to ask you like which step is fast or slow necessarily. It depends on a lot of other things. Like it depends on concentration. Like just like the fishing example, it depends on concentration. Depends on lots of things. But I could ask you this kind of question where it's like, okay, if you have O dot versus C dot, which one's more stable? Well, what's the difference? The carbon and oxygen. They're on the same row of the periodic table. Their major difference is electronegativity. Okay? A radical is electron rich or electron deficient? It's electron deficient. So which one do you think is less happy about being electron deficient? The oxygen is not happy about being electron deficient. The carbon's not either, but the oxygen is really not happy. So these are probably more, this step right here is probably going to be pretty fast, right, to get those things going.